Okay, good morning, everyone. So I want to start by going back to the scenario I talked about a while back, where I said Mr. Godber and I decided to play each other at table tennis 8 times. And I fancy myself as a bit of a good table tennis player, as I may have mentioned before. So let's say the probability I win each game is 0.6. We don't know how we worked that out. Perhaps in the past I've won 60% of the games we've played. And that gave us this distribution of binomial probabilities. And you may remember that I said we sometimes, in fact we always, tend to draw it like this. Bad maths, I know, because we're talking about discrete data, so you can actually only have these values. There's no, you can't have 1.5 wins, but there we go. Can I just say, no wins does have a probability. It's a very, very small probability, but it's not actually zero. So these are the different probabilities of the different number of wins. So, it is most likely that I will win 5 games. And we said that was because the expected number is always n times p, the number of whatever it is you're doing, games in this case, and the probability of success, which is 4.8. So that's 5 to the nearest whole number. But, there is a probability that I only win 2 games. There is a probability that I only win 1 game. It's fairly unlikely, but unlikely things do happen. And what we're looking at in this video is a process called hypothesis testing. And hypothesis testing is where you say, okay, this is what we think is true, but how unlikely do things have to get before we start saying, hang on a minute, are we sure that this is true? So, for example, if I play Mr. Godber 8 times at table tennis and I only win 2 games, do we just say, well, yeah, it's unlikely, but unlikely things happen? Or do we say, hang on a minute, maybe Mr. Cooper isn't as good at table tennis as he thinks. Maybe that probability isn't 0.6. And hypothesis testing gives us a way of investigating just that. So a hypothesis testing problem is always set out in a particular way. So here's the variable that we've been talking about. X is the number of wins when we play each other 8 times. And so that's referred to as the test statistic. We then say, right, what's the default belief? What do we think is true at the moment? And we think at the moment that the probability of success is 0.6. What's the alternative hypothesis? Well, we just have this sneaking feeling that I'm perhaps not as good at table tennis as I make out. So our alternative hypothesis is that probability is less than 0.6. And let's say, okay, we play each other 8 times and I only win 2 games. Is that enough to make us think, do you know what, he's not as good at table tennis as he thinks? Well, let's think about the probability distribution. Again, it's not symmetrical, is it? But I always, when I do a sketch, do a little sort of bell curve. I know that in this case, the peak is going to be at n times p, 4.8. So I know the peak is about 5. So an observed value of 2 is down here. But is that low enough to make me think, yeah, this can't be true? It's probably this, isn't it? How do I decide? And that's what hypothesis testing is all about. Okay, so what we do is this. We look at the observed value and we judge its probability against a significance level. Let me explain. The significance level is always quoted in the question, and the two most common are 10% and 5%. So at the 10% significance level, we look at our observed value and all the probabilities less than that, so the probability of 0 to 2 in this case, and we say, is this less than 0.1, 10% as a decimal? And if it is, if it's below this critical value, then we say, yeah, that's just too unlikely. Something odd must be going on here. He can't be as good at table tennis as he thinks. A 5% significance level asks a stricter question. Is the probability of 2 and all the values less than that, is it less than 5%, 0.05. Is it below this critical value? So that's a stricter test. We need more evidence at the 5% significance level. And if it is less than 0.05, we say, well, at the 5% significance level, we've shown there's something fishy going on. At no point in hypothesis testing are we going to prove that my probability of 0.6 is wrong. All we can do is we can say, right, we've got sufficient evidence to suggest that something is fishy. So bearing those two probabilities in mind, let's have a look at my situation here then. So here is the calculator set up for this problem. 8 games, probability of success 0.6. I want to work out the probability of every value between 0 and 2, which actually is just 0, 1 and 2, isn't it? So I put lower of 0, upper of 2. And that gives me a probability of 0.0498. So let's ask what's going on at the 10% significance level. Okay, so at the 10% significance level, this is less than 0.1. So there is sufficient evidence to reject the null hypothesis. Null hypothesis, remember, was that I'm better at table tennis than him. There's significant evidence to reject that and suggest that the probability is actually less than that. But actually, this is low enough for us to reject it at the 5% as well. Remember, at 5%, we're asking, is it less than 0.05? And it is, just. So even at the 5% level, there's sufficient evidence to reject the null hypothesis and suggest that I'm not as good at table tennis as I think. We have not proved that this is wrong. We have not proved what it is instead of 0.6, but we have started the process of thinking, right, something has got to change. Let's look at a second example. So here's a question where we first got to sort of pull out what's going on, what are the parameters here. So a certain doctor is undertaking research with a new drug, and he's testing 20 patients. And he reckons that his probability of success previous to this experiment was 2/5. So let's say that X is the number of patients who are successfully treated, and that he's testing 20, and his probability of success is 2/5 or 0.4. He thinks that the new drug represents an improvement on the standard treatment. So what we're dealing with here is a null hypothesis that the probability is 0.4. That's our sort of status quo, that's where we were. But now look at this. The alternative hypothesis is that the probability is greater than 0.4, which is different to the previous example where we thought it was less than 0.4. We've got an observed value of 11. So let's sketch this on a graph. Again, we know this isn't symmetrical, but we're just doing it quickly. So 20 times 0.4 would be 8. So we know the peak is at 8. So clearly 11 is above that. But the question is it too unlikely that you would get 11 successful people being cured with a probability of 0.4, or does it suggest that the probability is greater than 0.4? We're being asked to test at the 5% significance level. So we're being asked to test, is this equal or greater than or less than to 0.05? Remember, if it's less than 0.05, then it's just too unlikely, and we're going to reject the null hypothesis and accept the alternative hypothesis. If this probability is greater than 0.05, then we're going to say, yeah, okay, it's unlikely, but it's not unlikely enough, and we will stick with our null hypothesis. So let's enter the variables on our calculator. So this time we need 20 as our number of trials, and the probability is 2/5, 0.4. And can you see the difference this time? We're not looking at the bottom end, now we're looking at the top end. Now the maximum value is 20. You're only testing 20 patients. So this time I'm looking for the probability between 11 and 20. So my lower is 11 and my upper is 20. And recognising whether it's an upper tail or a lower tail problem is one of the skills you need to develop, because they won't tell you. You have to sort of glean that information from the question. Here we go. So that probability is 0.1275. So it's 0.1275. Now 0.1275 is much bigger than 0.05. So what we say now is that there is insufficient evidence, should have written this beforehand, to reject the null hypothesis. With that result alone, we haven't got enough evidence to say this test has improved. We would need a lot more evidence. Doesn't mean that the test hasn't improved, but with that value alone, testing at a 5% significance level, it's not enough evidence to suggest it needs to change. Okay, so here are two further questions on a similar theme. Press pause, have a go, and then as the video continues, I will show you the answer. Okay, so here's the first one. We're rolling a dice 12 times, and probability of getting a 6 is 1/6, classic binomial problem. But we've only had one number 6, so we're testing. Is the probability a 6, or is there something dodgy going on? Is the probability less than 1/6? So null hypothesis, p is 1/6. Alternative hypothesis, p is less than 1/6. So we're looking at a lower tailed problem here. I know that with 12 rolls, I would expect the peak would be at 2, wouldn't it? So is 1 unlikely enough? So I've entered the values onto the calculator. I want the probability of 0 to 1, not just 1. I want all of those probabilities there. To enter 1/6, the fraction button doesn't work as it does normally, does it? You have to do 1 fraction button 6. You can't hit the fraction button first. Anyway, so 0 to 1, here's my probability, 0.3813. Now I'm testing at the 5% significance level, so I was checking if it was more or less than 0.05. It's much more than that. So there is, here we go again, insufficient evidence to reject the null hypothesis. Let's have a look at the second one. So the second one, no context here, so it's all a bit wordy. And do you notice they use a funny sort of thing here? They say x is taken from a binomial distribution where n is 20, but p is p, and then they tell you what p is down here. So I always sort of plug it straight in. And we're not being told what this is, whether it's a dice or people being tested for a new drug. It's just completely without context. We're told that the null hypothesis is that the probability is 0.3, and the alternative hypothesis this time is that it's greater than 0.3. So we're at an upper tail, and we're testing at the 5% significance level, which is 0.05. My expected value, 20 times 0.3, that's 6, so I know that 10 is above the peak, and so I want to know all the probabilities from 10 to 20, so I've got to get that into the calculator. So I've still got the last one here, so number of trials is 20, probability of success 0.3, and I want all the probabilities from 10 to 20, so lower is 10, upper is 20, and that's 0.047 so 0.04, so that's 80, isn't it, when I round it to 4 decimal places? Which is less than that. So this is really unlikely. So there is sufficient evidence to reject the null hypothesis and suggest that P is greater than 0.3. Again, no proof, but a suggestion that we've got a building evidence case. Okay, so just a little bit of practice of this from the textbook on page 106, exercise 7C. If I zoom in on that, then we've already done question 3, but if you have a go at 1, 2 and 4, question 4 has a 1% significance level, which is different, but I'm sure you'll be able to work that out. So that's exercise 7C, and that's on page 106. And then I also think it is worth going to the mixed exercise on page 109 and having a go at number 1 from the mixed exercise, and then over the page to page 110. It was question 3. Question 3, the first two parts, A and B, are a normal binomial question, and then they add the significance test thing at the end. So there's 5 questions for you to try. Answers are in the online textbook. If you haven't got access to the online textbook, please let me know, and well, you can read the questions from the video, but I can send you the solution bank so you've got the answers. It's Friday tomorrow, bank holiday, so no video, you deserve a break, but there is more to this hypothesis testing, so we will finish it off on Thursday and Friday in the following week. I trust you are all well.